Hey guys, so last time in my last video I gave you an overview of this particular project, and in this video I wanted to do more of an update on where we are on the wings, primarily the wings, and give you a little idea of the aerodynamics involved with a tandem wing plane. So we're going to take a look at the aerodynamics, we'll take a look at the wing design, and then we're going to come back to the shop and I'll take you through the construction process. Okay, so before we get into the construction techniques and the build of the wing, I thought it would be a good idea to take a few minutes and just go over some of the aerodynamics and some of the complexities of a tandem wing design. And this is going to be a very brief overview because this really can be a complex subject. So we're going to start with just a very simple traditional airplane design with a large main wing and a tail wing. And what we have here, we're going to have the weight acting down through the center of gravity and the lift acting up through the center of pressure on the wing. And this is an exaggeration. So, and this distance between these two forces is going to give us this pitching moment. It's going to want to pitch the aircraft forward. And in addition to that, we're going to have a little bit of pitching moment just due to the lift on the airplane as well. Now, this is going to want to pitch the whole aircraft forward, and we need to balance that somehow. And we can use this balance force from the tail. So basically, the tail is generating negative lift. It's actually pushing the tail of the airplane down, and because it's acting at a long distance from the center of gravity here, we have a long moment arm, so we don't need as much pressure in the back. And that's going to give us this balancing force. And then when the balancing force from the tail matches the pitching moment from the wing, then we end up with this level and trimmed flight. Now this gets a little more complicated when we're talking about a tandem wing because we don't have a tail. We have two wings. And here we're going to have the center of gravity acting down through the center, the weight, mass or the weight acting down through the center of gravity. And the center of gravity on a tandem wing is going to be somewhere in between the two wings. And I say somewhere because there's a lot of factors that go into where that center of gravity is or should be based on the center of lift, the distance between the wings, the angle of the wings, the ratio of the size of the front wing to the rear wing. So there's a lot that goes into it. So in addition to that, we have the lift acting up through the center of pressure of the two wings. Now, the center of pressure, basically, we're going to have an overall center of pressure, and it's going to be acting up and to the rear of the center of gravity, just like in a traditional airplane. And so we have this center of pressure and this pitching moment on the front wing and the rear wing, which gives us this large forward pitching moment, and we need to find a way to then balance that pitching moment. But in a tandem wing, we don't have a tail so we don't have this tail balancing force. So the way we do that is by adjusting the angle of these two wings. So you can see we're ending up with a slightly larger angle of attack or angle of incidence on the front wing and less on the back. And the idea here is that we're going to be generating more lift on the front wing and a little bit less on the rear wing. This is going to give us that corrective pitching moment. Now, this is also the reason I know I mentioned in my first video that a tandem wing plane is really not the same efficiency as a single mono wing of the same combined length. And that's one of the reasons for that, is because this rear wing is doing less work. So that's putting a higher wing loading and more pressure on the front wing. We're generating a little more lift on the front. So we're losing some efficiency there. So this is the design I've come up with. And you can see that the front wing is a 26-inch span, rear wing is a 35-inch span. Now, I know this is probably going to drive a lot of you guys nuts, but I have a tendency to mix my units, so I'll work in feet and inches for some things and in grams and kilograms for another. I'm sorry if that is annoying, but a lot of the published information that I use, comes from different sources, and some of it's in imperial, some of it's in metric, and rather than spend a lot of time trying to convert everything to one, my brain just kind of runs through and mixes units. So what I've chosen here is a distance between the wings is 18 inches. So that's from center to center, front to front. The wing chords are 4.5 inches. Now, what I set out to do when I started this design was I wanted a high aspect ratio wing because I wanted something that was going to be efficient. I really didn't care about maneuverability. The whole idea behind this is a very efficient plane at cruise. I wasn't worried too much about slow speed characteristics because it's a VTOL, so really it's going to transition. It can transition at speed, or the motors can partially transition. So I wasn't really worried about the slow speed characteristics as much. So what I ended up doing was picking my chord and my overall wing length, and that would give me a wing area. So that's my wing area of 275 square inches. I've got an aspect ratio of 13.6 if I combine the wings. So really that's a high aspect ratio wings. We're getting into glider territory there. But by the same token, my wing loading is 22 ounces per square foot, which is a high, kind of a fast sport. Like I said, I was going for something that's going to, cruise at a relatively high speed and be efficient. Now, when we take all of this into the design, the hardest part of this was balancing those pitching moments. And what I did was I ended up setting my wings here at 2.5 degrees in the front and 1.75 degrees in the back. I wish I could say that I sat down and did all the calculations and this is what I came up with, but the truth of the matter is that I modeled this in XFLR5, set up my span and my wings, and did the whole plug and pray. Multiple iterations at different angles, different heights, different separations, different wing lengths, spans, front and back, till I got something that worked for what I needed. So this is what I came up with, and basically at about 1 degree of angle of attack for the plane, my pitching moments completely cancel out. So I think with a little bit more work, I probably could have gotten closer, but then I'm starting to get to the point where it's just not buildable. My accuracy of the building and getting these angles exactly right at this scale probably negates a lot of the real fine detail design work that I could come up with. So what I chose for a airfoil is this NACA 23018. I like this NACA series of airfoils. I generally prefer something like a 23015. I really like that airfoil. It's a very low drag, kind of a low pitching moment, good stall characteristics. I've used it on a number of builds. but I went with the 018 because I needed this thickness here. And I'll explain that a little bit more when we take a look at the wing design. Okay, so we're back in Fusion here and we're taking a look at the design a little bit. And I think I showed this in the first video, but what I'm going to do here is I'm going to go ahead and turn off fuselage, and I'm going to turn off the stabs in the back. Okay, so let's take a look at the wings. Like I showed you in the diagram before, we have the front and rear wings. This is at 2.5 degrees. This is at 1.75 degrees. And I have, so anything that you see in this gold color is going to be printed. Everything else, this gray, is fiberglass. And the reason I did these printed beds is it's a lot easier if I want to change something to reprint something than it is to create a new mold and new castings and layup and all of that. So if I need to change these wing angles during testing, I really can just come in and reprint these wing beds at a different angle, and we're good to go without having to rebuild everything. I'm going to go ahead and let's shut the wing beds off, and let's take a look just at the front wing. The two wings are going to be constructed the same way, but I'm going to shut off the rear wing back here, and let's take a look at the front wing. Now, the front wing here, you can see I've actually cut out where the aileron's going to go. This is, I take that back, this is the front wing, so this is actually the elevator here. But we'll take a look at this. Now, this wing design is a hollow wing design, and it is something called, basically the technique I'm using is a stress skin. So unlike traditional aircraft structures, let's go ahead and take this front wing top off, and you can see the structure inside. In a traditional wing design, something that you would see in a traditional aircraft or an older aircraft would be a very rigid internal structure. So you'd have a lot of ribs and a large spar, multiple spars, and that structure would resist the loads, the lift loads generated by the wing. And in those cases, then you would use, you could use a flexible covering, thin aluminum or, cloth, mylar, something like that, in a traditional build. Now, in a stress skin design, what we're doing is we're building some of that strength into the skin itself. And actually, the skin is going to take the primary load. And what we need to do with the internal structure is primarily just separate those two skins and keep those two skins apart. And this is going to work, and I know people hate this analogy, but it works kind of like an I-beam in that we have a rigid, stiff skin on the bottom, and we have another rigid skin on the top, and then we have this shear web in the middle. And different from what a traditional spar would be, which in a traditional spar would handle that, would be a large beam in here that would handle that bending stress. Here we can use a much smaller, lighter structure inside, and really its primary job is to keep the top skin and the bottom skin separate, so that the tension and compression forces in those two skins can operate at a distance. So we're going to have under normal load in an airplane here, we're going to have a tension force in this bottom skin, and then we're going to have a compression force in the top skin. Okay, so we'll have tension down here along the bottom, compression on the top, and we have this light structure in the middle that basically keeps our separation and keeps the wing in shape to resist that load. I've probably done a horrible job explaining it, but we'll take a look at that a little bit when we get down into the shop. Now, basically, I've got these holes on the end, and this is for a 12mm carbon fiber tube that is just going to span here and extend out the end, and those will be the mountings for the motor pods. Plus, it being a tube allows me to run the wires through the wing and out into the motor pods. What we're looking at here is a couple of holes so that I can bring the wires out to the servo that will be back here. And I'll go ahead and show you, I've got a servo bracket here, and we'll just turn off. I lose myself here. So it's the front wing top. We can turn that on, and we'll turn the bottom off. So if we look down here underneath, I have these servo brackets, and if I shut off the fairing, basically this will house the servo, will sit right in here, and the wires can come through, and they'll come through two holes here in the center of the wing down into the fuselage. And then I've got a servo fairing. These again should be gold because they're going to be printed. And this fairing basically does two things. One, it holds the servo in place. So if I were to take this off, I could just pop the servo right out. Plus it adds a little bit of aerodynamic fairing here over the linkage coming out. And that's pretty much the wing design. And we'll go take a look at that in the shop. All right, so we're back downstairs in the shop, and during the explanation that I butchered during the design on the stress skin and how the I-beam structure works, I figured that the easiest way to explain it is a piece of corrugated cardboard. We've got the corrugated cardboard, we've got this paper on top and a paper on the bottom, but then we have these corrugations in the middle, and these act like a shear web. So they are going to separate the two layers of paper and give us some pretty good rigidity this way. And if we go this way, you know, these are running in this direction, much like our wing. They're going to give us a lot of strength this way. But if we come in and just strip the paper off, right, you can see that the paper itself, not very rigid, not very strong, good strength and tension, nothing in compression. So, like I said, this is pretty much how the wing structure works, where these shear webs are like the structure inside the wing, and then we have the top and the bottom skins. You're going to see, though, that that's also how we make up the skins. The wing skins themselves are essentially, if you will, these corrugated pieces. We'll take a look at that. To start the process, what we need to do in a fiberglass layup like this is we need to build molds. And in order to build the molds, we need to build what's called a plug. And this plug is essentially a replica of the wing that we want to make. This is cut out of the green rigid insulation from Lowe's, covered in a layer of fiberglass and resin, sanded down, and then I've got this primer on it and sanded this down. You can see this one has not a great finish on it, but it was good enough for this initial testing. You can see I had a little trouble getting it out of the mold here. This stuff is pretty strong, but it's not great in tension. It's good in compression, but not great in tension. So the idea is that we create this, this wing plug, and then we make a mold out of it. And the way we make a mold out of it, so this is the fuselage mold that I'm in the middle of working on. So this is the fuselage plug. And it's in this box and would have had a parting plane in here, which is just another melamine surface in here to split this mold in half. Essentially what we're going to do is we're going to create a two-part mold. And if I turn this over, you can see that I've got one side done. And then what I do is take that parting plane out. And then we'll put some release film in here, mold release. And then we'll start laying the mold on this side. This red is just a thickened resin with a red dye, so that when I'm laying this up, I can see that I'm getting good coverage, as that red will come up through the cloth, see through the cloth as we get the resin in. So, and then we'll build this up, crack it open when it's done, and hopefully pull the plug out as few pieces as possible. Okay, so for the wings, for the front wing, I did all of that, and these are the molds. And if you take a look at the mold here, you can see that you've got the wing shape in here, and these are open-ended molds because my wings are open-ended. So what we do for this is we start with this cloth, and my layup actually starts with a spray coat of that gray primer, and that's going to be my exterior coat or my paint or gel coat. And then we lay in this very thin cloth. This is 25 gram or 75 ounce cloth. It's nice, light, good tight weave. It fits conforms very well to the shape of the wing. But even with just resin, this is not going to be, these strings, not going to be very strong. In fact, this is what it would look like. The glass, 25 gram glass with the resin, and that sits right in here like that. And I'm using this carbon fiber toe that's laid in here to give me extra strength and tension over the top of the shear web, which is going to run right in here. But as you can see, that while it's good in tension, it's crappy in compression. So what we need to do is we need to stiffen that up. And like I said, that not only is the wing, but the wing skins are made out of this kind of I-beam construction. And this is Nomex honeycomb. This is the aerospace grade, 1.8 pound per cubic foot. And this is a 1/16 of an inch or 1.5 millimeters thick. And then, so this would sit in here and form that corrugation in the corrugated cardboard example. This is the corrugation, and that's going to separate my two layers of cloth. And this cloth would then go over the top, wet it out with resin, of course, and then these both halves would go into the vacuum bag and cure for 10-12 hours, somewhere in there. I'm going to give credit to this layup recipe to Rene, and I'll butcher his last name, Rosentrigger, I think. I think he's in Germany. I'll link to his channel in the description. He does a lot of great stuff with a VTOL, a fiberglass VTOL EDF forward swept jet. Pretty amazing. So this is his recipe, and he's been great about answering all my questions and everything. So definitely go give his channel a like if you don't already know who he is. So back to the layup. So we're basically taking this and we're creating this. So this is the top skin, the full top skin, where you can see we've got a layer glass on the back, bottom, a layer glass on top, and the 1.5 millimeter honeycomb. And not only is this good in tension, but it's good in compression. Good, pretty strong in flex and torsion, but much stronger than, the individual ingredients. So then this is going to form this is our top skin. This is our bottom skin. This is another example of Nomex honeycomb. This is commercial grade, 3 pounds per cubic foot, and this is a 3 millimeter, and we use this for something else. So now that we have this, we have the skins, the next step is the internal structure and the shear web. Okay, so now the shear web. This is the first try. This is 3 millimeter plywood, and it has been cut on my Shapeoko CNC router. And while it does fit in here, and this would be glued in, and then the other face would be glued on top of it, this ends up being about 50 grams. So this is actually weighs more than the skins. I mean, this skin is 31 grams here. So we needed to lighten this. This is the next version, and this mirrors the design that you saw on the computer. And this is, again, 3 millimeter, but I've cut out unnecessary parts, and then I just went nuts drilling a bunch of holes in it, and luckily the router takes care of all those holes for me, so I don't have to worry about it. This brought us down to, I forget, 25 or 30 grams. So, you know, it's considerably lighter, but still a lot lighter. Actually, I take that back. I think this was 38. So definitely lighter than what we had, but still too heavy. And there's too much strength in there. There's more strength in that than this wing really needs. So any weight that's left on the table is, you know, anything more than what you need is too much. So what I ended up doing was building this. Now this is a fiberglass honeycomb panel made up of this 3 millimeter honeycomb, a layer of 25 gram glass, top and bottom. And this is pretty strong, you know, in bending, and certainly on the short side, you know, the bending is very strong, and that's all we really need is we need the strength here, which this is very strong compression this way, which is the primary force. But we also need it to be a little strong this way so it doesn't flex. Even though the top and the bottom are glued in place, we wouldn't want the middle to buckle and allow those two skins to, you know, to come close to each other and ruin the structural integrity of the wing. So this is when I cut all the pieces out of here, and I just, once I made this up, I put it on the CNC router and cut it just like the plywood. These were 8 grams for all of the internal structure, so I was very happy with that. It glues very well inside the frame, so I'm happy with the way that that works. And we end up with a wing that's very strong, very light, which is the goal here, especially when we're building this small. Trying to build in fiberglass at this small scale and be very light and efficient is very difficult. And as we start to get a little bit bigger, then we'll get some economy of scale, and the volume to the surface area will start to change. So in the end, this is what we end up with. This is the final wing. Well, it's the final test wing. This is the front wing. It is very strong in tension. It's very strong compression and bending. It's very strong in torsion. So I'm very happy with the way this came out. The wing itself came in under 100 grams, which was my goal. Here you can see the printed wing bed, and this is the front. So this is at the 2.5 degrees that we talked about. This has the carbon fiber tubes already epoxied in. If you can see it, but you can see that black stripe, maybe that is the carbon fiber toe in the structure. And then I have the ailerons already, or elevators, cut out. And the elevators are going to be made from these. This is the green rigid insulation with a layer of cloth and resin, and then a carbon fiber toe. And these are about half the weight of the elevator that would have been here had I gone with a live hinge. These will go with 3 Robart hinges, I believe, in here is what I'm going to do. and those will give me my elevators. If I turn this over, you can see we've got the mounting holes. These holes are to bring the wires from the motor and the servo down into the fuselage. And these are the little servo holders and fairings that I showed you upstairs on the computer. These will get glued in, and then the servos will get set in, and the fairings will get screwed on. Those hold the servos in. So yeah, really happy with the way this came out. Nice and light, extremely strong. And if you're wondering just how strong, some of you may have caught the video that I put up, but essentially this is a first test wing that I did. I was impatient. I didn't let the glass cure all the way before I started building it out and putting it under vacuum, so I ended up with this imprinting through, this dimpling. And you can see here I've got the glass panel structure in here. This whole wing, this whole plane should be in the 3-pound range. So each one of these wings should take about 1.5 pounds of load. So, you know, I wanted to do a 5G test, so 5 times that 1.5 pounds. And I would have been happy with that. I set it between 2 bricks and put weight on it. I actually ended up taking this all the way up to 23 pounds here in the middle. So that's about a 12 or 13G load. So this is actually stronger than I need. But at this point, I'm not sure how much lighter I can make it. So we're going to run with that for now. We'll see how it goes. Plus, you know, I'm thinking we're going to be doing, you know, testing, vertical flight testing, horizontal flight testing. Yeah, the way my testing goes, I may want that 12 or 13 Gs. I might need it. At 13 Gs, this bends, it flexes, but as soon as the weight's removed, it returns back to its zero shape. So it's definitely an elastic deformation and not a plastic. You know, there's pretty good force in there. So really happy with the way this is turning out. Where do we go from here? I think next step is I'll probably do a video on the nacelles, the design of the nacelles, the tilting mechanism. I'm printing those, and that's been kind of an adventure. Plus, I've been doing some motor testing and prop testing on the test stand that I have from RC Benchmark, and I've been doing some testing, you know, with the motor tilt, running at full throttle. So I'm really happy with the way that's working out. So next video will probably be an update on the nacelles and a quick look at where we are. Probably, you know, get started on the rear wing layup here now that those molds are done, and try and finish up the mold for the fuselage. Questions, comments, please put them below. I'm always, like I said, I'm kind of making this up as I go, so any constructive criticism is welcome. Anybody just wants to chat, let me know. And with that, I will catch you guys on the next one.